The Fundamental Theorem of Calculus, Part 1. Alright, so let's recall that if big F prime of x equals little f of x, the indefinite integral of f of x is given by the integral of f of x dx equals big F of x plus c. So we concluded our study on derivatives by taking a look at antiderivatives, or general antiderivatives, or what we're more likely going to call them, indefinite integrals. And then we switched gears and we started talking about sums and areas of rectangles, and then we defined a definite integral using this notation of this elongated s. Now we're going to make the big connection here. Why do we talk about general antiderivatives or indefinite integrals, and what's their connection to finding the area underneath the curve, or a definite integral? Well, their connection is established in the Fundamental Theorem of Calculus. So we're going to look at the Fundamental Theorem of Calculus, Part 1. It says we're going to assume that f of x is continuous on the closed interval from a to b, and let big F prime of x equal little f of x on the closed interval from a to b. Then, what must be true is that the integral from a to b of little f of x dx can be found by taking the general antiderivative, big F, and substituting in the top limit of integration, the upper limit of integration b, and subtracting from it the antiderivative, big F again, with this time the lower limit of integration substituted in. And a shorthand notation for how we're going to write this is the general antiderivative, f of x, big F of x, evaluated from a to b. Now, informally, the Fundamental Theorem Part 1 says that we can evaluate a definite integral by solving for the antiderivative, big F of x, and then substituting in the limits of integration, b and then a, into the general antiderivative, f of x, and subtracting. So notice that there's no constant of integration when evaluating a definite integral. So we don't put that plus c that's associated with solving an indefinite integral. So remember that the answer to an indefinite integral is a function, but the answer to a definite integral with limits of integration is a number. So that's why we're not going to have that plus c. We want an actual concrete number to be the result. So instead of using geometry, that's all we had so far. So to find the area under a curve, so far we could either use geometry if we had perfect geometric shapes and formulas in which to use, or we could go through the long process of using the limit of Riemann sum, so the limit of those rectangles getting really, really small. But now we can use the Fundamental Theorem of Calculus Part 1. We don't have to do any of that. We can find the general antiderivative of f of x and then substitute in the limits of integration and subtract. So we'll go ahead and go through quite a few examples of this. This is going to be what we do for a few different sections, and we're going to start learning about strategies for finding more indefinite integrals or more general antiderivatives so we can apply them to the Fundamental Theorem of Calculus to help us solve definite integrals. Alright, so some examples. So I'm interested in the integral from 1 to 3 of x squared dx. So before just using the Fundamental Theorem of Calculus, which is huge, I cannot stress enough how important the Fundamental Theorem of Calculus is, I want to talk about our previous strategies for this. So if we just quick sketch this, I have the integral from 1 to 3 of x squared. So here's the x squared function. I only care what's going on between 1 and 3. So first of all, this does not form a perfect geometric shape that I can just have a nice geometry formula for. Instead, I would have to use my limit of Riemann sum. So I'd have to create a bunch of rectangles and then evaluate that limit. And we really didn't even go through strategies on how you evaluate the limit of each of these rectangles getting smaller and smaller in width. So as of right now, we don't even really have a concrete strategy for finding the exact area under the curve, just an approximation using rectangles. And we know the more rectangles, the better. Well, now we don't have to be concerned with any of that because we can instead find the general antiderivative of the integrand. So going back to antiderivatives, the antiderivative of x squared, we can use the power rule for integrals. So the general antiderivative is x cubed over 3. So remember, we add a power, add 1 to the power, and divide by the new power. And then normally we would say plus c, but that's what makes a definite integral different. We're not going to add a constant. Instead, we're going to say we want to evaluate this general antiderivative from the limits of integration from 1 to 3. So we're going to first substitute in the top limit of integration. So we plug in the top one, the bigger one first. So we're going to have 3 cubed over 3. So we substitute it in 3 for x. And then we subtract, substituting in the lower limit of integration. So that's going to be 1 cubed over 3. So now here, 3 cubed, so we get 27 over 3 minus 1 over 3. So since we have common denominators, we get 26 over 3. So now what we just did was find the exact area under the curve. So all of that work was leading up to a formal definition of a definite integral, and then the fundamental theorem of calculus, which gives us a really nice formula of how to relate the antiderivative concept to finding a definite integral. So now let's try another example here. We have the integral from 0 to pi over 4 of secant squared x dx. So first, we find the antiderivative of secant squared x. So the antiderivative here, what did I have to take the derivative of to get secant squared? So that function is the tangent function. So we need to evaluate the tangent function, tangent x, from 0 to pi over 4. So remember, no plus c. This is a definite integral. And now we need to substitute in the top limit of integration first, the upper one. So tangent pi over 4. And then we subtract, plugging in the lower limit of integration, tangent 0. And now we evaluate. Using our knowledge of trig functions, we know tangent pi over 4 is 1 and tangent 0 is 0. So the answer here is 1. So the area bound by the curve secant squared x on the interval from 0 to pi over 4 is exactly 1. And now let's evaluate the definite integral from 1 to 4 of 3x to the 1/2 plus 2x. So first, the general antiderivative of the integrand. So what we're going to have is 3, we're going to just leave the constant, x to the, if we add 1 to 1/2, we're going to get 3 over 2. And then instead of dividing by 3 over 2, we multiply by 2 over 3. And then plus 2x raise the power by 1, divide by the new power. And we're evaluating this from 1 to 4. So let's simplify the general antiderivative before we substitute in the limits of integration. So we're going to have 2x to the 3 over 2 plus the 2's cancel here, x squared, evaluated from 1 to 4. So now we first substitute 4 into the general antiderivative. So if we substitute in 4, we're going to have 2 times 4 to the 3 over 2 plus 4 squared. And all we've done is substitute in the 4, the upper limit of integration. And now we need to subtract, plugging in the lower limit of integration into the general antiderivative. So we're going to get 2 times 1 to the 3 over 2 plus 1 squared. So now we need to do some simplifying. 4 to the 3 over 2, remember, is the same as 4 to the 1/2, which is the square root of 4, which is 2. 2 cubed is 8. 8 times 2 is going to give me 16. 4 squared is 16, and 16 plus 16 is 32. Minus, and then here I have 1 to the anything gives me 1, so I'm going to have 2 plus 1, so I'm subtracting 3 here. So that must mean that my area is 29. And I'm done with this definite integral. So now let's try one with an exponential function. I have the integral from 0 to 2 of e to the 2x dx. So here the general antiderivative of e to the 2x is 1 over 2 e to the 2x evaluated from 0 to 2. So my rule tells me that I'm going to substitute in the top limit of integration first. So I have 1/2 e to the 4, because if I plug in 2, 2 times 2 is 4, minus, and now I have to substitute in 0. Now, a lot of people get in the habit of they see a 0 and they think, oh, well, if I plug in a 0, it's just going to make everything go away, so I don't even have to worry about this part. But you have to be careful. An exponential function raised to the 0 power, or any number raised to a 0, gives me 1. So this would be 1/2 e to the 0, but this is not 0, e to the 0 is 1. So it's going to be 1/2 e to the 4th minus 1/2. And if this were a question on the AP exam that was multiple choice, it would probably be simplified to 1/2 times the quantity, e to the 4th minus 1. So I'm going to factor out the 1/2 that's common in both and leave 1/2 times e to the 4th minus 1 as my final answer. Alright, let's take a look at the formula for the definite integral of f of x equals 1 over x from a to b. So if I have the integral from a to b of dx over x, I get out the natural log of b divided by a. So I just take the upper limit of integration, divide by the lower limit of integration, and that goes into the natural log function. Now, this is a formula that you can memorize, but I'm going to go through the next example of showing where this formula comes from. So here I'm interested in finding the integral from 2 to 5 of dx over x. So if I didn't know this formula existed, I should know that the general antiderivative of dx over x is the natural log of the absolute value of x. And then the fundamental theorem part 1 says I want to evaluate this from 2 to 5. So I go ahead and plug in the top limit of integration, the natural log of the absolute value of 5, subtract from it, substituting in the lower limit of integration, natural log of the absolute value of 2, and now, well, 5 and 2 are both positive, so I have natural log of 5 minus natural log of 2. And so there's a property of logarithms that says if I have the difference of two logs, I can turn this into one log and write what I'm evaluating as a quotient. So natural log of 5 divided by 2. So the general rule over here, and I'll just rewrite it to remind you, if I have, let's say, log base a of x minus log base a of y, so as long as they're logs with the same base, here I have natural log, so they're same base e, then I can turn this into one log with the same base, where I take x and divide it by y. So this was a property of logs that I had. I also have, if this is a plus, then it's log base a of x times y. So I had these different properties of logs. So that's where this formula here is coming from. So notice I could have jumped straight to solving this problem as a natural log of b over a, 5 over 2, exact same answer. So if you don't remember this formula exactly, then it takes this extra step of understanding that you can combine two logs that are being subtracted and turn them into the log of a quotient. In the past few examples, we've been using the Fundamental Theorem of Calculus in a very straightforward way. So now we're going to look at a further application of using the Fundamental Theorem of Calculus Part 1. We're going to be given the fact that big F prime of x equals little f of x, and we're going to be given the fact that the integral from 2 to 7 of f of x equals 9. Now, if big F of 7 equals 4, find big F of 2. So let's start by writing what we know. We know that the integral from 2 to 7 of f of x dx equals 9. But here's what else we know. We know the integral of 2 to 7, well, remember that the integral from 2 to 7 of big F of x dx, I can apply the fundamental theorem of calculus to this in a general way by saying that this is equal to little f of x's antiderivative, which is big F. So this is the same as big F of 7 minus big F of 2. And this has to equal 9. But I've also been given that f of 7 is 4. So here, this value of f of 7 was given to me as 4. So 4 minus f of 2 must equal 9. So now I'm just solving an algebraic equation. If I subtract 4 to the other side, I'm going to get negative f of 2 equals 5. And then I'm going to divide both sides by a negative, so I get f of 2 equals negative 5. So the value of f of 2 that I'm searching for is negative 5. So this is an application of the fundamental theorem part 1, but I'm using it in a different way. So it's understanding that if I'm given big F prime of x equals little f of x, and I'm given this definite integral from 2 to 7 of little f of x, then I'm really being asked to write out the Fundamental Theorem of Calculus Part 1 in general terms to search for one of the missing components. So they could have instead given us f of 2 and then asked us to find f of 7. We still would have had enough information to do so. Alright, and finally for some assorted AP multiple choice questions. So here, the integral from 1 to 2 of 4x cubed minus 6x dx. So just to take and point your quick attention to the fact that this is number 1. So this was the very first question on one of the past AP multiple choice exams, indicating that they consider this to be a pretty basic problem that you can guarantee will more than likely be on your test as well. So first we take the general antiderivative. So this is going to be 4x to the 4th divided by 4 minus 6x squared divided by 2. And this has to be evaluated from 1 to 2. So let's simplify here. We have x to the 4th minus 3x squared evaluated from 1 to 2. So if I substitute in 2 first, I'm going to get 2 to the 4th minus 3 times 2 squared. And all I've done is substitute in the top limit of integration, and then I need to subtract if I plug in 1. So 1 minus 3. So here I'm going to get 16 minus, here I have 2 squared is 4 times 3 is 12. So 16 minus 12 minus, here I'll get negative 2. So now on the inside I get 4 minus negative 2, which is 4 plus 2. So my answer here is positive 6. So the answer here is C. In this next example, notice that again this was number 1 on a multiple choice exam from a past AP exam because of how straightforward it is. So it's a definite integral from 0 to 1 of the square root of x times x plus 1. So here the first thing I'm going to want to do is, instead of considering this as a product, I want to distribute in the square root property or the square root function. And I want to write this as x to the 3 over 2 plus x to the 1/2 dx. So I'm distributing in the square root function. So this is x to the 1/2 times x to the 1. So I add their exponents. That's where the x to the 3/2 came from. And then plus x to the 1/2, distributing in the square root function. So now I'm going to take the antiderivative. That'll be x to the 5 over 2. So I add a power. Now I'm going to multiply by the reciprocal, 2 over 5, plus x to the 3 over 2. And then I multiply by the reciprocal here, so that would be 2 over 3. And this evaluated from 0 to 1. So if I substitute in 1, I'm going to get 2 over 5 plus 2 over 3. And then I'm going to subtract, plugging in 0. So here, when I plug in 0 for both of these x's, I will get out a 0. So now I'm just trying to combine these two fractions. So the common denominator is going to be 15. So the top here is going to be 6. And then here, if I have 15, then the top here is going to be 10. So I get 16 over 15 as my answer, which is C. Alright, and so now a final look at an AP multiple choice question. So here I have this graph. Here's x and here's y. So here's my function, and they've been really particular about some of the points that it goes through being on this grid that's drawn for us. And it tells us the graph of f is shown in the figure above. If the integral from 1 to 3 of f of x dx equals 2.3 and big F prime of x equals little f of x, then what is f of 3 minus f of 0? So let's go ahead and write down on the bottom what's going on. So the integral from 1 to 3 of f of x dx, well, I know that that equals 2.3. But because big F prime of x equals little f of x by the Fundamental Theorem Part 1, I also know that this is the same as f of 3 minus f of 1. So f of 3 minus f of 1 is going to give us out a value of 2.3. But that's not exactly what we want. We want big F of 3 minus big F of 0. Well, if I wanted to write this in notation of a definite integral, what they're really asking me to find is the integral from 0 to 3 of little f of x dx. Well, remember that I can split this up into the integral from 0 to 1 of little f of x dx plus the integral from 1 to 3 of little f of x dx. Now, the integral from 1 to 3 of little f of x dx was given. It was given to me as 2.3. So now the question becomes, how do we find the integral from 0 to 1 of f of x dx? Well, that's where the graph comes in. So notice that between 1 and 3, again, we're looking for the area under a curve. So the area under the curve between 1 and 3, well, that one had to be given to us exactly, because since it is a curve, I wouldn't be able to explicitly find that without knowing the function f of x. But here, they've made it clear to draw the function between 0 and 1, or the portion of the function between 0 and 1, as a perfect horizontal line. So if I want the integral from 0 to 1 of f of x dx, I'm really searching for the area of this rectangle here. So this rectangle has base 1 and height 2. So 1 times 2 is 2. So the total integral from 0 to 3 of f of x dx is 2 plus 2.3, which is 4.3. And when they're asking you to find f of 3 minus f of 0, it's really going back to your knowledge of the fundamental theorem of calculus, because the integral from 0 to 3 of little f of x dx is the same as big F of 3 minus big F of 0. So the answer here is 4.3, and it really combines your knowledge of two things: the fundamental theorem of calculus, part 1, and the notion that the area under a curve is what an integral represents graphically.